I'm very happy to introduce Johannes Braumann, who's the one who made the KUKA PRC plugin. But not only that, he is also one of the heads of Robots in Architecture, Association for Robots in Architecture. And I think it's really related to what we've been doing and what we hopefully are going to do in the near future. And also, I'm kind of curious what is the concept of your presentation. But you've got your time, you've got your half an hour, and then a Q&A. So just for you to know how you're doing with the time.
Thank you very much. So thanks for the invitation. I'm really happy to speak now because you already heard quite a bit about robots from Stuart, from Alessio, so I can now really build up on that. The topic of my talk today is robotic craft. I want to look a bit into how we can translate basically manual actions into robot actions, basically thinking about what can the robot do, what can't the robot do. So hopefully this will also give us some range for discussion afterwards. So together with my colleague Sigrid Brell-Cokcan, we founded the Association for Robots in Architecture in 2011 as a spin-off basically from the Technical University of Vienna with the goal of making robots accessible to the creative industry. Basically as a platform for both for our research but also as a network for all robot users, as you're going to see right away. Sigrid is now head of the chair for individualized production at RWTH Aachen in Germany. I'm currently a visiting professor at the University for Arts and Design, where we're setting up a laboratory, a robotic laboratory, together with the Ars Electronica, with KUKA, whose German headquarters right next door, Austrian headquarters right next door in Linz, and one more university. In the past years, the robots in architecture has really exploded, so it's a really big community. It started out quite small with just a few European and American universities, but now it has really become a wide network with many researchers, with many disciplines and many people working on extremely different topics, which is very exciting for us. As a network of robot users, we try to keep track of these robots, but we also host every 2 years a conference on robotic fabrication in architecture, art and design, ROBARCH, and we also then every 2 years publish a book with Springer. The next ROBARCH conference is going to be actually not that far away, in March 2016, and it will happen at the University of Sydney. So if you're interested in the general topic of using robots in architecture and have got time shortly before the Easter holidays, it should be quite a nice trip. We have all the workshops happening right at Sydney Harbour, so directly within the city, and it should be quite exciting. These are some of the workshops from the video from the last ROBARCH that happened at Michigan in the United States. So here they did robot welding basically, and for example then we also had Bot and Dolly with us. You know them, for example, because they got the Oscar with Gravity and were recently bought by Google. Anyway, we saw quite a few robots today. In my particular case, when I talk about robots, I would always mean robotic arms, like you see here, for example, from KUKA. So basically, they're modeled after the human arm with, in this case, 6 degrees of freedom. We've seen a similar picture like that before already, so we know them mostly from the automotive industry. But we think they're really interesting for the creative industry as well. There's a number of reasons for that. On the one hand, we have the very large workspace, that the machine is not built around the workpiece, like a 3D printer, where you have such a machine, but you can work on such a scale, where you actually have the machine inside its own workspace. Then they're very cheap and affordable. So Jan, I think you got yours for free, more or less. Even if you have to pay money, I know people who bought barely used robots for just around 20,000 euros, which is still quite a bit of money, but compared to other machines, it's really, really quite cheap. Of course, an obvious advantage is the multifunctionality, that an arm is just a universal tool. So whatever you mount on it, it's going to become that machine. It becomes a welding machine, it becomes a milling machine, it becomes a 3D scanner, or it can become an entirely new machine. What's really nice about that is that robots are really proven technology. They are not experimental, but they really have been developed for 30 years or more, and they're developed to be as sturdy and as reliable as possible. So when we as architects, as designers, work with robotic arms, we can really focus on the programming, on the actions, but we do not so much have to focus on actually getting it to work, but we can really go very deep into the digital programming without having to think about too much about the physical robot. With physical robot, I only mean the robot itself. Of course, we have to consider the physical properties of material and so on. Finally, which is also nice, is that robots are available in many sizes, which is quite special for such kinds of machines, that with the same programming, with the same code, you can drive a very small tabletop robot, or you can also drive a very huge robot like that one. This was a KUKA Titan, it can lift more than 1 ton. So this makes quite a difference. So you can, for example, at your office, prototype things in small scale and then translate them into large scale at the fabricator using the same programming environment and so on. Now, well, why doesn't every artist and designer have their own robot in the workspace, in their workshop? There's a very easy solution for that. Is mostly about the programming. Because of course the programming that comes with the robot, so that you can buy from the robot manufacturers, it's focused on the core robotic markets, which at that time is still mostly the automotive industry. So the software works in a way that you can very reliable but very slowly program a cycle, then you test it, then you send it to the robot. With many industry applications, this doesn't make much of a difference, because even if the programming takes you a week, the same program is going to run for 8 years and going to produce huge amounts of money. So the small programming costs, and compared to the product, it's really tiny. For our purposes, of course, it's different. We like to work with prototypes. We like to work with single pieces. So here we really need workflows that allow us to keep the programming costs as little as possible. So for us, quite a few years ago, the solution was then to think about how can we integrate the programming into a flexible environment that would allow us to have this flexibility to do mass customization, to program a process only once, but be able to adjust parameters even afterwards. At the same time, we are also teaching very large courses at TU Vienna at that time with more than 60 students. So a challenge was just teaching the students 6 kinds of different softwares, which they weren't ever going to use afterwards. So for us, the solution for that was to use Grasshopper, a software that you all know, with the idea that we can teach students skills that they are still able to apply afterwards, no matter if they work with robots, if they work with other machines, or with something completely unrelated. It also gives us the possibility to have this direct feedback. Basically, the robot is there at the end of our parametric definition. Whenever we change something at the beginning, we're going to see how it's going to affect the robot itself. Over time, the past probably 4 or 5 years, the plugin has really developed into a full solution so that we can simulate and work with a very large range of robots. We can use external axes if they are linear, if they're rotary. And we have this kind of direct feedback where we at all times see the entire toolpath of the robot. So whenever we change something, we see how the axis movement are going to change. If something is not reachable, we can just react to it and have this kind of direct feedback system. So somehow like you make a digital photo to see how it looks, and then you can react to it in a very intuitive way, make it brighter, make it less bright. Here it's more abstract, but the same concept applies. You get your feedback and you can react to it. You do not have to send it to the robot, see if it works out, but you can immediately work with it. For us, it's quite nice to see that this is now nothing that's only being applied for academia, for students and courses, but is really being used in industry, especially for applications where there isn't any particular suite of software. If you want to do only robotic milling, it makes perfect sense to buy a milling software and you will be really happy with it. But for many applications, like in this case, you want to do special things, you want to adjust, you want to create your own fabrication strategies. And here it makes sense to use a universe environment like KUKA PRC and do your program in that. So here this is Artist Engineering in Berlin. In that case they do hot wire cutting, they also did 3D printing and polishing and some more complex cycles whenever they are not milling with the robot. Some other project, for example, is here. We saw the 3D printed rocket nozzle, so they are working on similar laser sintering applications with titanium as far as I know, and also had the challenge of finding some way to control this cycle at a very deep basis so that they really can tweak every aspect of it and not have to rely on any automatisms. There are also more strange machines, for example here. This is a setup from the actual Argentinian nuclear agency that's looking into how robots can access areas that may not be accessible to humans. And again, they wanted to quickly test certain cycles, in this case mostly plasma cutting, and do this, couple this with their 3D scanners so they can find their workpiece, cut it, and then do the next part. And then the mechanical engineers actually again started using Grasshopper, which was quite fun to see. This is a company that I like very much. They're called Branch Technologies. You may have actually heard from them. They are an actual startup in the United States at Tennessee. And what's really nice to see here that this is a company that is really led by architects. So these are not mechanical engineers who look into large-scale 3D printing and get an architect to do some illustrations or to render some nice images. But this was really a concept, an idea by an architect who founded the company, who got venture capital. They now bought the entire setup and are also creating their toolpaths in KUKA PRC, testing and simulating it, and then fabricating it with the machine. So there aren't that many images out yet, but what I've seen is really quite promising, especially in the relation to the American construction market at the moment. To go a bit more into the topic of the talk, so is something happening? Do it like that, bit of sound. When we like to work with robots, when we do workshops, we always try to have this kind of link between the physical action and what you program. So in this case, that we had students really experiment with the material, try something out by hand, see how it reacts, what kind of geometries they can fabricate, and then only to try to apply that at the robot and to look into the actual special things that we can do with the robot, the things that can go beyond what you actually do by hand. So in this case, over about 4 days at the workshop at the RMIT in Melbourne, we created some kind of mass customized structure based on hot wire cutting. So the idea is we wanted to reduce waste as much as possible so that out of a minimum of material we get a maximum of structure. So in this case we wanted to work from all sides, so the solution for that was not to mount the hot wire cut on the robot like you saw with Artist Engineering before, but to actually have a stationary hot wire cutter and then have the piece mounted on the robot and move it through, allowing us to work from more sides as would otherwise be possible. And then over the next few days, we fabricated a large number of parts where, of course, every piece in that case was unique. Let's skip through that a bit. And then finally assemble it on site over just a few days. So really that you first look at the material, try to understand it, and then try to apply it with the robot itself. In an industrial research project called Arosu, we pursue the same kind of idea, the same kind of concept. That's a rather large consortium, so it's funded by the European Union, and it's a collaboration between mechanical engineers from TU Dortmund, with us as the Association for Robots in Architecture, with electrical engineers from Labor, and then with industry partners, KUKA, an architecture office, and most importantly in the lower right corner, a stone company. They're based in southern Germany, and they were actually the ones who had the idea for the research project. They've been working with robotic arms for more than 10 years now, so they're really one of the pioneers when it comes to working with robots with stone. And they're mostly using them for milling. So they have got huge robots where this is, that spindle is about that size. So they're huge machines, and they use it mostly for 3D milling. So they have their 3D scans from existing statues, for example, and then they cut them out. However, part of the market that's actually at least as important to them as these more sculptural applications is the structuring of stone. So if you look at castles, at churches that have natural stone facades, you will see that usually they have somehow been chiseled. So there's a large number of manual chiseling strategies that are employed for weather protection and all kinds of other purposes. And now they had the problem that for these many square meters of facades, it was hard for them to find specialized people who could do that, because you need masons who are highly educated, who also then cost much, but there aren't that many of them anymore in Germany. So the idea was to automate that process and try to find a robotic chiseling solution, more or less. So the first step in this case was again to look into how the manual process actually works. So in this case, the mechanical engineers from TU Dortmund, they made a very large testing bench. So they used 2 high-speed cameras with more than 4,000 frames per second, and they coupled it with a force torque sensor underneath the stone. So really, whenever the guy hit onto the block of material, they could see exactly how the tool moved in space, and also with how much force that was actually applied. They then created this range of analytical showcases, how they could work. And based on this force and trajectory data, at Labor they then built a prototypical tool that would exactly follow this kind of trajectory with a modular front piece that would allow it to be applied to multiple structuring strategies. So now the idea was, of course, the challenge was to find a way to program such a cycle, because there is no existing software for stone chiseling. So this was where we came in and basically worked with them to create a software, a plugin based on KUKA PLC that would allow them to at first work with the stonemasons, try to find out how the strategies work, to evaluate the surfaces, and then to apply that in the software. What was then nice for us to see, and this was actually the result of one of my mistakes, that we were programming. I wanted to rotate these things with certain attractor points, but then I switched the axis, which resulted in us not rotating in the plane but outside the plane, which in that case led to structures that were not regular anymore, but really three-dimensional. So something that, for example, could not be done by a mason, because if you hit the stone from the side, it's going to jump off, and you're probably also going to hurt yourself. So again, this was something that the robot could actually be used to realize projects that would otherwise be not possible by regular standard structuring strategies. So the video before was also a bit old, so by now it's been quite a bit faster, and we're working on this, making it really very, very significantly faster than any kind of human structuring strategy, basically. Another project that we have currently ongoing is more not as industrial, but more, let's see, why doesn't it start? Not as industrial, but this is arts-based research. There's a program for arts-based research in Austria funded by the FWF. And through this grant, where we applied to, we got a robot at the University for Applied Arts in Vienna. And the idea of this project is to take a robot, put it into an existing wood workshop at the university, and then to see how we can integrate it into that workshop. Not to replace the carpenters, but to see what kind of projects can we realize that would otherwise not be possible. So you see the kind of low-tech strategy, bring that in, and then into the wood workshop. Maybe some of you have actually been there. It's a very nice place to have at least 3 carpenters all the time on site, but they're not very heavy on CNC technology. So what they actually have is one machine that can only make 2D cuts of panels, which you need for exhibition, pedestals, and all the standard things, but they didn't have any CNC machines before. So the first thing we tried before we even mounted a milling spindle or whatever on it when the robot arrived is that for some reason at the beginning it shared the cell with a lathe machine, with a turning machine that you see here in the lower right corner. And the idea was to, well, just try out, mount a turning iron onto the robot and see what happens. Some of you are laughing, yeah, okay, with good reason. So basically, we thought, well, let's just mount it there, go there, start the machine, and see what happens. The result is aesthetically actually quite nice. What it does not show is that actually the metal piece, the robot didn't have this kind of sensitivity that you have as a carpenter. When you move the tooling, you feel the resistance of the wood and you react to it. What happened here is that, of course, we went into the material much too quickly. Basically, the metal got stuck. The machine then more or less ripped off the tool holder, which didn't impress the robot at all. The robot was just standing like this, and while it was flopping around on the front. So this was for us one of the first results, basically showing us that in some applications we can definitely replace the carpenters, but in others it's a rather bad idea even to try. We're also working with the Department for Geometry on that one. So we have mathematicians who are very much into industrial geometry. So they have also been working, for example, with Pottman's group, if you know them from Evolute Tools and all of that. So the root surfaces were a very big topic. So, for example, they've been investigating strategies that could be realized with the robot. And again, here was a really good collaborations between different strategies, because if you look at that one closely, what the mathematicians designed, you see that you actually have all the lines, or many of the lines, coming together at one point, which is not a problem if you have lines in CAD, but once you have a material thickness, once you have material collisions, you run into big problems. So I think this was also a very educational experience for all of them. The milling itself was done really quickly, and this was definitely one of the applications that's much quicker than doing it by hand. Basically, the robot just moves around here, makes his holes, and this was one of the first design pieces that our students then did with the strategy. That was more recently at the Vienna Design Week, where we had one stationary piece, and then we had like live fabrication sessions at the university with a coupled tool that basically was tool holder and milling machine all at once. Of course, the advantage of the robot is mostly its spatial awareness. It is, after all, as we heard, a positioning device, but it can do this very accurately and precisely in space. So, for example, it makes it very easy in Grasshopper just to say, well, I take this data from the image sampler, I have it adjust the depth of my cut, and then I get these kinds of pattern out there. One of these is actually now sitting in the office of the Austrian Ministry of Science. They gave it to him as a birthday present or whatever. We have a few quite nice collaborations then going on here as well, where we try to bring different disciplines together. We work with artists, but I think I'm going to skip over that a bit more quickly. This one was a collaboration with Rüdiger Suppin of TU Vienna, where the idea was to 3D scan a chair, then mill out pieces, and then afterwards reinforce it with a carbon inlay. This was a project from Lucy D, they're industrial designers, and they created this kind of wavy mobile structure for Rado, which apparently is a brand that sells expensive clocks. So again, the idea was here to really put this into parametric code and then explore the different strategies very quickly and very efficiently without having to manually put it into CAM software each and every time. That's a project that I like quite much. You may have seen the video actually, but this one probably not. Again, this kind of translation of human skills to robot skills. So we had a project together with Absolute Vodka, where the idea was that they had a limited edition of vodka, where every bottle is individual. So during the fabrication, there's this kind of blue paint put outside the bottle. It's then, when it gets hot, it basically gets permanent, and every bottle looks different. So the idea was to do that as a live installation, so that the robot would spray paint, in this case, on t-shirts. So these were our first experiments, and you can see without much difficulty that we are not spray painting experts. So when we just mounted the tool on the robot and started spraying, this is what came out. So we quickly saw that we need some professional help on that one. So we worked with a graffiti artist from Vienna who showed us then how he sprays. And if you look at it carefully, you see how he always controls the airflow very precisely at all time. So it is not just an on-off operation. All the time he says how much pressure, he defines how much pressure he wants, and this is how he gets his lines. However, this was a very last-minute project, so for us we couldn't really implement this kind of control. So we really wanted to have only on and off control. So in this case, for us, it was a challenge to find a strategy that builds upon the strengths of the robot, so that we do not try to exactly duplicate the manual spray painting strategy of the human artist, but to think about to take part of this knowledge, put that knowledge into code, but then optimize it for what the robot can do best. In this case, this kind of very precise close movement. So the idea was then that we just were able to just take a picture on the street of people, and then after 5 minutes they could walk home with their spray painted individualized t-shirt. So this was then shown at Vienna at a couple of occasions. So this was close to the Museumsquartier. Then we were also at the museum, at the MAC, at the Museum for Applied Arts, and at a few more locations. And actually it turned out that all the programming was actually one of the smaller problems. The main problems we had during the event was actually just the paint clogging, because usually again the spray paint that just sprays very hard, clears up the nozzle, but in this case we always had one person on site taking care of the spray guns. Finally, I don't have that much time anymore left, so try to make this one quickly. This is a project that's a bit of a larger scale. It's a project we did with Neugebauer and Köhldorfer, the artists in Austria, and they are specialized on aluminum casts. So they made aluminum sculptures, and at one point they proposed to Red Bull to build a monumental 70-meter high sculpture on the Formula 1 racing track. So they basically designed it, they made all the 3D data, then they sent it to a manufacturer, and then they got back a quote for around 70 to 80,000 euros to fabricate only the positive molds. Red Bull has got plenty of money, as you know, but in this case it was just too much, so they had to look for alternate means. So what they then actually did is that they saw that here in Vienna we were working with industrial robots, so they simply went to an automotive company in Germany, they bought a robot, put it on the truck, took it home with them, set it up, and once they had it all set up with all the fences around and whatever, they actually noticed that it's not as easy as taking a 3D file, copying it onto the robot and pressing fabricate. So at that point, they asked around for how much milling software costs, and it turned out that the milling software is more expensive than the entire robot itself, the one they bought. So for them it was really now a way to find some way to fabricate it, and KUKA, probably knowing that they wouldn't have any much more money anyway, forwarded them to us. So we developed a kind of optimized grasshopper workflow for them that would allow them to do all the operations that they need, just look at it in the simulation and then fabricate it. For us, it was really nice to see, as you saw from the image, they managed to do that, but what was really nice for us to see was that we worked with them for only about a week, so 4 to 5 days. We showed them how to use the robot, how to use Grasshopper, how to do the programming, and then they were able to do this by their own. The guy who did it is the one in the red suit, and in his case, he actually studied tourism before he started working with his father on that project. So he didn't have any robot knowledge. He has never used Rhino before. He just looked into the things that he needed. He probably didn't know how to draw a curve in Rhino, but he knew how to program the robot to do the things that he needed to do. The pieces were then shipped to Germany, put into sand beds, and then cast at a foundry, then sandblasted, and finally assembled on site. As the last project, which may take slightly more than 15 seconds that I have, is one of the projects that I recently advised at the University for Arts and Design in Linz by Benjamin Kreimer. We had a project that was called Machinic Food Design, where the idea was that students look into investigate, look into this kind of, in a very general field of food design, think of new applications, how the robot could be used. So this was really our first attempt to get the students at Linz involved with robotic fabrication. So again, we really looked for a topic where they could experiment and fabricate at home without having a robot, that they think of certain processes and only then apply it with the robot at the end of the process. So in this case, the student thought about printing, 3D printing liquid in liquid. So the largest part of the semester he actually spent in his kitchen mixing up different mixtures of additives to the liquid to keep it stable enough, but not to make it look like jelly, to think of ways how he could inject dye without it dissolving in the liquid. Finally, he managed to do that. And what I really like is how he then managed to really turn this from a university project into an actual business model. So he handed it in for a competition and was chosen to represent Austria at the Design Week in Sao Paulo in Brazil. He then also got the money to make the entire end effector more professional looking. So here on the left side you see this is really just an Arduino board with one servo motor pressing upon, I think, a gifted syringe that we got from somewhere for really cheap. And then he managed to do this in a very professional way. And this is now part of his promotional video, where he tries to then really turn this into a business, to showcase this at events, and to then also build upon that. And I think it's really nice to show how it's mostly good enough to have a really clever idea. The robot programming in this case is really simple. You just have your points, you say move from here to there and inject in between. So in this case, it's really about giving people the tools to realize these projects in a very intuitive and easy to use fashion. Thank you very much.
Questions?
Just wait a minute. I have one. How do you coordinate the motions of the arm with some other output, like making those drops, for example, or I don't know, something that needs to go on and off when the robot moves?
We actually try to keep everything as simple as possible. So in that case, with that project, it's really just one wire going from the robot to the Arduino board, and basically just a digital signal saying either on or off. And whenever it says on, it basically rotates the tool a little bit further and puts another drop into it. The more professional version now works slightly differently, but in this case, when we program it, we do not need any kind of feedback from the Arduino. So it's really just a static process where you say this is the shape we want to achieve. We could import any kind of mesh geometry, any kind of point clouds, and then just click play. So that's the nice part about it. Interactive things are always a bit more complicated. So we're now actually with KUKA, robots it used to be a bit more complicated. We're now working with them to create a solution to stream data back and forth in a very safe way. There are already ways to do that, but they are quite involved and they could damage the robot. So now they're working on a new way, and we postponed it a few times, but we're definitely presenting it in March at the conference, and by then hopefully the underlying KUKA software will also be available. And then you can really, for example, if you want to do it all in Grasshopper, get your data back via Firefly and then react according to it, or however you want to achieve that.
Also, you have been probably asking because we don't have the opportunity to get any feedback from the robot, so we cannot control our effector.
You can. You should use the serial port with the older ones.
We are missing something, some part of the hardware at the robot, as far as I know.
No, but there is with the old ones, there's a regular serial port on the PC side. I'm quite sure it is, also with yours. And you can just send any kind of string back and forth. It's actually quite useful.
We should have it got much sooner than
So, I mean, and this is kind of a what's next question, but in a much more articulated way. I think we're all pretty used to the one-armed robot, but the new AB that's two-armed, which I'm assuming KUKA down the road will have a two-armed. What do you think the ability of a two-armed robot will be over the one-armed robot?
Actually, I have to admit I'm not too fond of the idea of two-armed robots, because they are really made for the simple idea of taking a human worker, putting him out, putting the next one in, and then they're usually not even that much faster. So it's really just about they don't need a brake, so they can do it at the same speed and so on. So also the ABB Yumi was really built for the electronics industry. So this is for ABB, the target market, where they just have, like at Foxconn and other companies that you know from Asia, they're just also looking to automate things. And they have now this kind of two-armed robots that are also then force sensitive. So the idea is that they can then really feel this kind of snap connections that they work with. It could be interesting for architecture, but in general, I'm not really sure if this is the best approach. In general, I have to say that robots, like industrial robots, just in general are the second best choice. You can always build a machine that does one thing better than the robot. There's hardly anything. The powerful thing, I think, for us, for experimentation, but also then for applied stuff, is really that they are cheap, reliable, and multifunctional. So I think this is what makes it powerful. Also for many companies, they could just always have somebody build their own machine for 300,000 euros, which then only they can support. So in many cases, it makes more sense just to get a robotic arm, which may not be as accurate, but at least they can quickly replace it. They have exchange parts on stock and all of that.
I'm just curious, which kind of liquid was this for the printed drink? It's not water, right?
So basically, I think what he used for, fortunately I don't know it myself, so I don't want to spoil his business secrets, but I think what I'm saying is pretty obvious anyway in this case. So for making it thicker, there's some regular commercial thickening agents, which they, for example, also use in homes for the elderly to make it easier to swallow and all these things. So this is like a medical product or like from the regular industry, and then all the drops, they have to have some kind of oil content inside so that they do not immediately mix with the liquid outside. But this was really his main work over the semester, to find a mixture that would allow it to work. So you can imagine the first few tries, he made the drops and then they sank to the floor and were all assembling down. And then the other ones, when you drank it, you thought you were drinking some kind of liquid jelly and was really disgusting. So this was finding the kind of compromise between something that works but at the same time is still aesthetic somehow and something that you would like to have. This was the main challenge. Now it's really nice. You can really take these ones, you can move it around, and you see it always bouncing back into the original position. And I think after 3 or 4 hours, it starts sinking down. But
what was he studying?
Industrial design, actually. So we're now working at the Art University with actual more industrial designers, which is quite nice to see because they have a stronger focus on the digital side of things. So the architecture education there is a bit more traditional, while industrial design is really forward-looking and into many different kinds of software, from SolidWorks over different automotive software, simulation and all that stuff. So it's quite nice, and the robots fit really well into this kind of industrial design scale, while for architectural purposes they can work on components and all of that, but you don't really build your house with a robot unless you have some kind of really fancy rail system. But in an industrial design scale, you can really fit your entire furniture piece, your entire prototype, or whatever you want to do. You can often fit it inside the workspace, so it's quite fun for them. And for us as well. Good.
Thank you very much.
Okay, thanks.